Mr. Klein here, still technically not wearing a hat. And we are going to do a little bit of work that's going to help you understand how to complete your homework tonight. So I'm on this page in our note packet, and we're going to look at how to draw the graphs of the derivatives for four functions. A lot of strategies we're going to mess around with today. So what I would start with is this. Look at this curve. This looks like a cubic function. And so the first thing we know is that f is cubic. If it's cubic and it has a degree equal to 3, then the derivative will be a quadratic because it will have a degree that is 1 lower, right? All right. So we know we're drawing the graph of a parabola, which represents the derivative graph for this. So call that the first thing. Second thing is identify where the derivative will be 0. I see a 0 for the derivative here and here at the two extreme values, at the relative maximum and at the relative minimum. What I like to do, and other good students like to do, is I draw a couple of vertical lines at those points, and it helps keep us organized. First, it makes sure that I mark here and here that these are places where the derivative will be 0. The other thing we can say is that we know that the graph we're about to draw of the parabola, increasing means positive, decreasing means negative, increasing means positive. So we know that our graph is going to go like this. Now, what we don't know is how far down to go. So there's going to be a vertex somewhere around here. Is it, right here and the graph is shallow? Or is it way down here and the graph is very deep? Well, one of the things we learned in our last lesson was that that vertex, that minimum on our derivative graph, is going to happen at the point of inflection. So I would counsel you to come up here and identify where your point of inflection is happening. Right about there. And what you want to do at the point of inflection is take out your straight edge and draw a tangent line. Now, I know that this is not a perfect science and that all of our answers aren't going to be exactly the same, but what I drew right there looks like a pretty good tangent line. Recall that at the point of inflection, the tangent line will cross through the graph so that it will be above it on one side and below it on the other. You should be able to identify the slope of that line. What would you estimate is the slope of that line? I'm getting that the slope is about -2. And what that means is that the derivative is -2 at this particular instant. So at this x value, I'm going to come down here to where y equals -2. And that's where I am going to put our vertex. Well, we could keep doing this, right? We could keep drawing tangent lines and estimating the slope. But I think that if you found these two zeros and you found the minimum, that's good enough. Draw a graph that goes positive, negative, positive. There's our quadratic. Next one, what kind of graph are we looking at here? That's right, f is a sinusoid. Sinusoid is the name for anything that is either a sine or a cosine function. What would you predict f prime is going to look like? All right, here we go. So step number 1, identify where the slopes are 0. So boom, 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 boom. Mark each one of them. With a vertical. Again, the vertical is just to keep yourself organized, not actually part of the graph. 0, 0, 0, 0, 0, and 0. Lots of zeros on this one. Okay, let's pick an interval. Let's pick this one right here. On this one, can you see that it goes from being concave up to concave down about midway between these two zeros? So somewhere around here. Since it's increasing, this would be our steepest positive slope, which means that it will be a maximum. And let's see, I'm getting that the slope is about 2. So up here at this x value, I'm going to go up, 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 up. Here's 2. And I can connect those. Okay. Rest of the graph. Hopefully we can see that if we were to go right here, we would get another point of inflection. And that point of inflection has a slope equal to -2. So I'm going to mark a point on our derivative graph at -2, which means we get something like this. And that pattern, because of the repeating nature of this graph, is going to continue all the way across. So our derivative function, which I just drew, is also a sinusoid. Now they're getting interesting. So this is a piecewise function, right? If you look over from here to 2, 2 is a pretty important point on this graph. I'm going to mark 2. We can see that this is linear. So let's just take the linear part. If the function is linear here, what do you know about the derivative? That's right, the derivative is going to be constant. Now, if it's constant, we need to figure out what that constant value is. And we do that just by looking at the slope. So if I look at the slope here, it's going up 1 over 1, up 1 over 1, up 1 over 1. So the slope down here is 1, which means that the derivative graph is going to have a constant value of 1. Look right here. We've got one of those pointy spots. Do you remember the name of those pointy spots on the graph? This is called a cusp, and we know that at a cusp, the derivative does not exist, or the derivative is undefined. Doesn't matter which. So I am going to add, as soon as I see a cusp, an open dot right there. And now we have half of our derivative graph. Let's get the other half. On the other side, we can see that it is quadratic, right? And if it is quadratic, the function, then its derivative will be linear. So we're drawing a line. 2 things you need to know about that line. First, if you're drawing a line, you only need 2 points, right? Connect them. Second thing, it does not need to connect to this. And in fact, it shouldn't. And I'll explain why in a second. So let's get 2 points that are going to be on this parabola. I'm going to go for an easy one. Right here, when x is equal to 4, I can see that the derivative is 0. So I'm going to mark a 0 right here. Now, the other thing that I am going to note is that the function is decreasing and then increasing. So the line I'm going to draw will be negative on this side of the 0, and it will be positive on this side of the 0. So it's going to go something like that, which is why it can't possibly touch this part of the piecewise curve. Let's pick a point. So I've got 1, I need another one. Doesn't matter where you pick. I'm going to say I'm going to go right here at, what would that be, 5, 6, at 7. And I'm going to draw a slope, something like that. And then I'm going to count the slope. Your slope might be a little different than mine. It's okay. I'm getting a slope of, let's see, over 1, up 1, 2, 3, 4, 5, 6, 7. That's a coincidence, by the way, that x was 7 and the slope was 7. So I'm going to go 1, 2, 3, 4, 5, 6, 7. And then here's what I'm going to do. I'm going to draw our line. There's a really common mistake that I'll see folks just draw that piece. It has to go all the way back to x equals 2 right here. Boom, 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 boom. And when you get to x equals 2, since we know that the derivative does not exist at the cusp, it must have an open circle right there. So I know this is going to be weird, but since the derivative does not exist, there will be no filled in circle at either of these spaces. Last one. On the last one, I'm actually going to pause and see how much of this you can fill in on your own. So hit the pause button, start playing with this one. All right, let's see what we've got. Here's what I filled in. I filled in that I know the derivative is 0 at this minimum and 0 at this maximum, and that right here where the function is constant, the derivative will be 0. Another thing we can go ahead and fill in is that up here, the slope is -2. Therefore, the derivative from 1 until 4 will also have a value of -2. Now, right here, you got kind of this weird thing going on where the derivative was quadratic and it became linear. So I think what I'm going to do is say at this linear chunk right here, I don't know exactly where it begins and ends. Right there, the derivative is 1 because it's up 1 over 1, up 1 over 1. So I'm going to mark 1. Boom, boom, boom. If the function doesn't exist, neither does the derivative. So let's put a hole right there. And then at some point, it stops being linear. It becomes quadratic. So I'm going to go down like that. And then I know it's negative. I'm just going to go something like that. All right. So that gives us everything but this weird little chunk. Now, this is the weirdest part of the graph. I'm going to draw a line here and a line here. At this instant right here, the slope is like a vertical line, right? It's vertical. One of the things you probably learned back in algebra is that a vertical line has an undefined or an infinitely large slope. So it's really, really infinitely big. And then immediately it's positive and big, but decreasing, 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 decreasing. Look at these slopes, decreasing, decreasing, decreasing until 0. So I have to draw a function that is really, really infinitely positive and then decreasing until it hits 0. That would look something like this. If you got that, that's really, really, really good. In fact, the back of the book for this made a mistake on it. Other side's going to be similar. It is 0, negative, more negative, really, really negative, really, really, really unbelievably negative until it is infinitely negative. So you'll see this go something like that. In summary, I would like you to pause the video and see if you can fill in the blanks on this sheet. Here are your answers. And then I'm going to move up, so pause the video if you need that for longer. By up, I actually mean down. There's the rest of the answers. If you are good on everything that you've seen here, then you can stop the video and start on your home fun. If you would like to hang around for an explanation, I'm going to go through each one of them. First one, self-explanatory. Second one, remember that if you have a maximum or a minimum, then the derivative is 0 because the slope of the tangent is 0. Next one, recall that if you have a point of inflection, which is when the concavity changes, that means that you have the steepest slope, which means the slope is at a maximum or minimum. If you have a cusp on your graph, you can't draw a tangent, so the slope and the derivative are undefined. If a function has no value at a point, then it can't have a derivative, so the derivative is also undefined. If the slope is 0, like it is for a constant graph, then the derivative is 0. If a function is linear, then its slope is never changing, which means it's constant. Quadratic has a degree equal to 2, which means that the derivative has a degree equal to 1, which means that it has to be linear. Same game here, drop the degree by 1, so the degree would have to be 2, which means that it's quadratic. Next one, if the derivative is 8, that means it must have come from a degree that was 1 larger, hence the 9, 8 plus 1. And finally, if a function has a discontinuity, any kind of discontinuity, I'm going to draw a step 1 right here, then it's impossible to draw a tangent at that point, which means that the derivative is undefined.